3.3 recursion tree method. In this part, we need to do analysis on the solution we just derived in the previous video. But I want to introduce a new method. So it is not a rigorous mathematical method, but it is a simple way to estimate the efficiency. Yeah. Much simpler, but using our computer science analysis. We know we do not need a very precise calculation. So we allow some small errors, small minor terms we can ignore. Yeah. So using that way, we estimate the dominant term part. So we can get a growth function. Yeah. Our goal, we just want to get a growth function of the algorithm. Yeah, that is enough. Yeah. All right, so let's look at the new method. Yeah. First, we need to derive recurrence relation from the partition. Yeah. So we get that partition. Now, we just get the recurrence equation. Yeah. Equation, but here it is not that equation, it is inequality. It is still okay, inequality. Yeah, we can use the similar way to, similar to the recurrence equation way to estimate the function value. All right, yeah. S of n. Selection problem, the solution, S of n, we represent the number of comparisons to solve general selection problem with n data size, n elements. All right. To do that, divide and conquer, we split into several steps. So let's look at the number of comparisons for each step. All right. Cost breakdown. Yeah. Because we need to do some calculation to help us get the terms. Yeah. First, find the R medians. How many comparisons do we need to find R medians? Answer is n. Why n? Because n equals 3R. There are R groups. Each group, we need 3 comparisons. 3 times R, that is n. Okay, yeah. All right, so in our inequality right-hand side, n plus. Next step, compare 2s unknowns with m star. Yeah. This step, 2s unknown. So 2s comparison, but 2s approximately 1/3 of n. 1/3 of n. The reason n approximately 6s plus 3, right? In our assumption, 3s plus s. So 2s approximately 1/3 of n. Okay, yeah. Yeah. So we add this term. Next one, find the median of the R medians, R group medians. Recursion, so remember the recursion, right? Recursion, the data size, what is the data size? Data size 1/3 of n, but based on our recurrence, the function definition, S of n over 3. So we add it to the inequality right-hand side. Then, after that, what do we need? Okay, all right. We need to draw one of the two subarrays and do recursion on the other one. But when we drop, by elimination, what is the size of the remaining subarray? What is that size? Okay, yeah. The size at the most, right? At the most 2n over 3. Why at the most? The subarray that we drop it has the size greater or equal to n over 3. 2s plus 1, 2s plus 1, yeah? This 2s plus 1, this is approximately 1/3 of n, okay? Yeah. So we can at least drop 1/3 of n. The remaining, the worst case, right? Here we consider the worst case. Yeah. Because we have to take care of the worst case. That's the bottleneck. So we have to take care of the worst case. Yeah. All right, so that's why we add s of 2n over 3 back to the inequality. Okay, yeah. Initial condition, easy to get, right? Yeah. Then I just simplify the inequality so we get this inequality. The next step, we use the recursion tree to estimate s of n function. Here you can see if we do not use the recursion tree, it could be pretty hard to solve, to estimate s of n. Yeah. All right. But when we use recursion tree, it is pretty easy. Yeah. All right. Recursion tree method. We draw the tree starting from the root. Root is our s of n function. Then, based on this equation, you can see inequality. Yeah, not the equation. You can see two parts. The first part, non-recursion term, 4n over 3. That's the non-recursion term. Yeah. So we can add that part directly. Then, two recursion terms. Two recursion terms. All right. So let's do this way. Yeah. Two branches corresponding to two recursion terms. But the non-recursion term, we need to add to the, we need to accumulate non-recursion term. Accumulate. So we put there, yeah, for accumulation. Yeah. Then each node, we can make that split and get its corresponding recursion, non-recursion term there for later accumulation. Yeah. Similarly, for that, but these two non-recursion terms, we can add together to get a total non-recursion term of this level. Yeah. Then we can go down more and more. So you can see how many levels can we go down? How many levels we can estimate? The number of levels, approximately log n. Yeah, log n. Yeah, because you can see, divided by 3. So division. Yeah, so it's a log function. You divide the problem size by a constant. Divide problem size by constant, right? Yeah. Although here multiply by 2, but we just use this way. Use this branch to estimate the bottom level, right? So log base of 3. Log base 3. You will reach the bottom. Yeah. So it's a log function. Okay? All right? Yeah. Then accumulation, each level non-recursive term the same value, 4n over 3, but you have this many levels. So you can estimate S of n is in this big theta of n log n. But you can see that's still not quite our goal, big theta of n. So we cannot get what we want using this 3-element partition. Still a little short. Yeah. This factor still there. Yeah. We don't want this. Yeah. Because if we allow this log n, we just sort it. Right? At the beginning, we just sort the array. We can already get this kind of performance. But our goal is the performance big theta of n. Linear performance. Yeah. So what should we do next? Right? What should we do next? Should we throw out this method? But this method is pretty smart. Although a little short from our desired solution, a little short. Can we improve it a little bit to get the desired solution? Yeah. So here we do not throw away, yeah, because this method, this smart method, the reason is we do 3-element partition. That's too rough. We want to improve that estimate, or we want to tighten the estimate. So how do you tighten the method? Yeah. Change from 3-element to 5-element partition. Each group has 5 elements. If each group has 5 elements, can we improve the overall efficiency? Yeah. Let's take a look. So we go through the same method another time. The only change is from 3-element groups to 5-element groups. All right, so in our last video, we will do it. Yeah. All right, so